Swayam Prabha. Digital India. Educated India.
In the last class, we had defined a very important parameter which we called as understeer gradient. We looked at it from a state space form. The equations were written in a state space form. And we found out that this understeer gradient plays a very important role in the stability of the vehicle. In fact, if you go and look at that equation again, we see that BC alpha r minus AC alpha f is the key term, and the whole concept of understeer gradient is based on that particular expression, right? So that's what is going to make it positive, negative, and so on, right? Then we moved over. We haven't yet given a very physical meaning to it. We have not given yet. We said that that's definitely a parameter which has a problem, or which is going to create a problem on the stability of the vehicle, right? We also made it very clear that it is not that when it is negative, the vehicle immediately becomes unstable. We also said that there is a speed, a critical speed, okay, at which this vehicle becomes unstable. Okay, that's what we said. In other words, we had two terms, and we have to make sure, or we have to get that sum of those two terms to be negative in order that it should be unstable. This is where we left, and then we started with another small digression on steady state cornering. In order to, why are we doing this? In order to understand what physically this understeer gradient is. Okay, we will go back to the state space. We're going to spend some more time in state space. I know you've done this in controls, but we will go and refresh your memory on the state space as well. Okay, before that, let us look at this. So since I said steady state, okay, we do not have those terms. I is at r dot does not exist because it's a steady state expression. So we have an expression of this form. These are the two equations. In other words, the governing equation now, differential equation now reduces to these two equations. Okay, because this r dot, and we said that v dot goes to 0. Okay. One of the key things that we found when we started writing down this equation is that the two forces, that is force acting in the front and the other acting at the rear. Okay. Remember that we were looking at the bicycle model, and remember that we have one wheel or one tire where the left and right tire actually is collapsed. Okay, there was some confusion. I said front and rear in the sense that front and rear has one tire where the left and the right tires are collapsed into one. So the stiffness of this tire is the sum of the stiffness of the left tire and the right tire. In the same way it is for the front. So if you're given, say, in a problem the stiffness of a tire, then you have to take it as 2 times that of the stiffness of the tire, right? Okay, so that's just a small input. Remember that one of the key factors or key conclusions that we made was that the front and the rear centripetal forces are distributed in the same fashion as that of the weight of the vehicle, right? So we said Wf is equal to W into B by A plus B and so on, and it's distributed in the same fashion. So Fyr can be written, okay, like this. This is what we wrote, clear, and Fyf is written in this fashion. So in other words, mu squared r, that's the term, that's like our W, A by A plus B, and that is equal to B by A plus B. Okay, so you can write that as WR into U squared, okay, substituting it, and you can write like that. That's a very straightforward expression. Okay, why are we doing this? We'll know that in a minute. Now, this is also things which we wrote in the beginning of this derivation, that the forces that are acting can be expressed in terms of the stiffness. Okay, so in other words, we are using a linear model for the tire. Right. Now, let us substitute these expressions. Okay, here all these, this 1, let me call that as 1, 2, and 3. Okay, let me substitute that, so that now I will write this as FYF by C alpha F minus FIR by C alpha R. Okay, that would be the first two terms. Note that one minus cancels out and so on. Okay, even if you had written alpha F to be positive, you would get the same expression. Okay, plus L by R. And note that L by R is in radians because we are replacing the angles. So if you want to put it in degrees, correspondingly, you will make the changes. Okay. Now, let me substitute that expression, this is what we have here, from 1, okay, onto the new expression, which we would call as 4. Right? Substitute it and write it down. You will get a very interesting factor then. You will get m into, no, it's clear? I'm substituting these two into that expression. Okay? In other words, I'm going to take here first these two expressions and then substituting it there. Okay. Let's see what you get. Expand this. You will get BC alpha R minus AC alpha F. Wow. So that's what is the key factor here. Right? BC alpha F minus C, this is BC alpha R, sorry, BC alpha R minus AC alpha F is a key factor here. That will be divided by, we have A plus B, so A plus B, which is L. A plus B is nothing but the length of the vehicle, L into C alpha F into C alpha R. Okay, multiplied by that U squared by R is there. U squared by R, that's the term here, plus L by R. Let me call that expression phi and spend a few minutes here. Look at this term here. Let me call that term as K1. Okay. He's a very close relative to K3. Why? It is just removed from K3 by that factor L. Go back and look at that. We had put L squared there, so factor L. Okay? So many people call this as an understeer gradient. Right? Understeer gradient. Now, look at that expression. BC alpha R minus AC alpha F is here. Right. And what is your conclusion from this? That when the understeer gradient is positive, is high, okay, is high, then for the same U, very simple, first expression, first things, for the same U, okay, you are going to apply more steering input. Right? That's the first right, the beginning. Right? We will also note that it is possible to express this in terms of W as well. We will come to that in a minute. Okay. Now, let's go into the details of this. Let's say that I am plotting U squared by R. Don't be surprised if they say that understeer gradient, okay, is expressed in terms of per g value. In other words, you can also substitute for instead of m, you can put a w, you can put a gr. Okay, that's also possible. That people call this as K2. Let's not worry about that right now. I just want to point out that it's possible to write that as well. Okay, now let us now look at this graph of. So this is for a steady state cornering. That's the result which we are looking at. Let's consider the simplest case. Understeer gradient is equal to 0. That means that BC alpha R is equal to AC alpha F. What happens? If I now plot this U squared R, this is equal to a constant, which is L by R, okay, the kinematic angle, that is a constant. In other words, when I take a turn, whatever be the speed, I will apply the same steering input. Clear? Okay. Now, let us look at a condition where K is positive. K is positive. So this is, yeah, BC alpha R is greater than AC alpha F, right? K is positive. Obviously, that's a straight line because I have plotted this as U squared by R, okay? So what happens now? That straight line would keep increasing. That's the L by R. That straight line keeps increasing. So what does this mean? That means that if I have to take a cornering, or in other words maneuvering, with the same R, for the same R, if I now increase the speed of the vehicle, then I have to increase my steering angle. So in other words, the steering input that I give depends upon the speed of the vehicle, and it increases with an increasing speed of the vehicle. Okay? So that's why we say that it is understeered. Okay? So I have to give more and more steering if I now increase the speed. Okay? Comes out very clearly from this expression. What happens if it is a oversteered vehicle? In oversteered vehicle, this quantity is negative. So when I increase u, since it is multiplied by a negative quantity, what happens to my delta? Decreases, because I've obviously look at it mathematically, it's just a straight line with the slope is equal to negative. So that guy goes now like this. Right? What happens? There is one value of this U squared by R at which delta that is required is equal to 0. In other words, you don't give any input to the steering, delta is equal to 0, and the vehicle takes a turn. Okay? So it takes a turn. In fact, you cross that and come down. What happens? The delta becomes negative. What does it mean? It means that if you are going to take a turn to the right, okay, you're cornering, you give an input to the left. Okay, you give an input to the left. Oh, right? It comes out very clearly mathematically that that's what happens. I know, puzzle faces I see, but it's very simple mathematically. Right? No, you're not convinced? Okay. Whenever mathematics gives results like this, you look puzzled. You really want to know whether it is true or not. Right? Okay, so you want to look at physics, what really happens. Right? First, let this get into our mind. Is this clear? Okay. Why is this happening? Let's go to this, my front tire. Let me put that front tire. Okay. Now, actually, it is this alpha F and alpha R which is playing the role of cornering. Those two guys are very important. Right? That's why tire is very, very important. Look at that. Tire plays such an important role in this whole handling characteristics. Very important role. Right. Let's for a moment look at this more carefully. Please note that the B into, first my second expression there, here, A into FYF minus B into FYR, okay, is equal to 0, right? Because that's a steady state, right? Okay. Now, coming back to this, remember my figure, that was delta, right? That was delta. And then I said that there has to be an alpha F that has to be created in order that, or that should exist in order that I develop what is called as the front force. Clear? Okay. So when alpha F now increases, which means that my expression is going to become more and more positive, okay? What happens? It is going now up. Note that this is the direction of travel, okay? Now, if I now keep going up, then I have to give more and more steering in order that I maneuver my vehicle, okay, to take a turn, right? So when alpha F is small, then already the guy is aligned, okay, towards that turn, and so delta needs to be small, right? At one point of time, what really happens is that this alpha F goes to the other direction, okay? If it is like this, then we get into a lot more trouble of instability, right? Because I have to now bring it back again. So heading becomes a problem. So that is what happens, and in other words, that's this alpha F, role played by alpha F, becomes extremely important. Clear? So the key factor here is this BC alpha R minus AC alpha F. That's a key factor here. Now, what is A and B? Remember that they are the CG locations. Imagine that, or why imagine? You have so many front wheel driven cars. Most of the cars today are front wheel driven. So in a front wheel driven car, what do you think will be the distribution of A and B? Will A be small or B be small? A will be small. So all front wheel driven cars are understeer cars. So the first factor, right, they will be more towards the understeer vehicle. The first factor that the vehicle manufacturer has to look at is what is this understeer gradient. Okay? Towards the end of this part, we will look at what are the tests that are used in order to determine this. Let's not right now worry about it. But we need to know that understeer gradient, okay, is an important part of the, or important characteristics of vehicle for handling. Do the manufacturers produce an understeered vehicle or an oversteered vehicle? They do not produce an oversteered vehicle. Okay? Basically because the worry is it can become unstable. It's very difficult to handle. Sometimes it can become counterintuitive. So all vehicles are understeered vehicles. They are not oversteered vehicles. Okay? Please note they are not oversteered. They are all understeered vehicles. Right? Now the question is how much understeer it can be. Okay? That's the important question. If it is, I want to be very safe and I want it to be highly understeered, then tomorrow the newspapers or the magazines which does a review with your vehicle will say that this car is a damn squib. It doesn't just turn. Okay, you need to apply so much of steering for this vehicle to turn. The response is very bad, and blah 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 blah. You are in trouble. So I can't have so much of understeer that the guy who is going to drive the vehicle, he keeps on steering, right? So that's a problem. It can't be an oversteer. It is just above the neutral steer. Okay, why is that people do not look at neutral steer? Basically because, look at that quantity, it is BC, alpha R and alpha F. Alpha F and alpha R, what are they? They are the lateral slip stiffness, as it is called. Okay, lateral slip, because lateral slip angle, lateral force versus slip angle, slope of that curve, so lateral slip stiffness. It depends upon so many factors. You know, it's a tire, so many factors. And it depends upon the inflation pressure. If you're not maintaining an inflation pressure, definitely your handling characteristics will be affected. Okay? Depending upon what is the inflation pressure, how that varies and so on, that will get affected. And A and B are not strictly a constant. As for a car, it may be a constant. For even that we can't say, because there's a small difference can be there. How many people sitting, how they are sitting, and all those things. Okay? But for a truck, definitely, for a bus, definitely it has an effect. Okay? So it can't be straight away a neutral steer, so it will be slightly understeer. Okay? So that's the importance of understeer gradient. It becomes extremely important also in rear engine cars, rear engine vehicles. Many of the buses are rear engine buses, so then you have to be very careful in looking at this quantity. Right? So because it's a bus may not have that much effect, because the passengers can be distributed and so on. But for a car, rear engine car, it becomes, many of the electric vehicles, for example, or small cars, very small cars, okay, are rear engine cars, in which case, okay, you will get this vehicle to be oversteered, and hence that will be a problem. Then it comes to the fact that what happens to a Formula 1 car? Formula 1 car, the driver just doesn't have the time, okay, to corner. No, he can't give so much of input, steering input, in order that he corners the vehicle. So he would prefer it to be oversteered. Okay. Yes, this is important, but these people are very well trained drivers, so they know how to handle it, and so the vehicle will become an oversteered vehicle. One of the interesting factors in India, especially in the truck market, is that they mix the tires, or in other words, they mix the radial tires with bias tires. Many times they use the bias tires in the front, the radial tires at the rear, and so on. Okay? That will affect the handling characteristics of the vehicle, because usually the radial tires have 2 times more lateral stiffness than the bias tires, and so mixing this is going to have an effect because of that factor. That can be a huge factor when it comes to the mixing. Okay. Fortunately, they have a radial at the rear and a bias at the front, okay, so the factor actually increases, so it's not a problem. But if it's the other way, then you will get into trouble. So it's better that when you mix it, you be aware that it will affect the handling characteristics. Of course, cars, no one uses bias tires, so it doesn't matter. But for trucks in India, especially, because about only 20 to 22% of the tires are only radial tires yet. In fact, some of the survey one of my students did, we found that only about 6% of the trucks which he inspected recently, they have radial in the front. The rest of them have only bias. So it's very important that we understand this factor. Yes.
In case of a tractor trailer, how do you actually decide these things? Because when you're loading and unloading, there's a huge difference in the
Yes, of course. So that's why I said this would vary. Okay, when it varies, so you have to know the limits and accordingly adjust that. So it's not one factor. Okay, that's why the handling characteristics depend upon the load, how it's placed, and all those things will have an effect. Okay, so that's important. Right. So that's the key factor on understeer gradient. So as I said, the way it is defined is different. Okay, you can define this like in W and G out and so on. So be careful when someone tells you a value. Okay, we'll do some problems later. You have to be careful and ask him what exactly is your definition. Okay, I have got into trouble like that before. So you have to clearly know how someone defines the understeer, okay, gradient. What is the formula he is using? So it can be K1 or it can be K2. For example, you can put W here and take this G out and then write this whole thing. Now delta is equal to, let me call that as K2 in that case, K2 into AY plus L by R, where AY is the lateral stiffness, okay, expressed in terms of G. In terms of G. So radians per G is what you would say is the unit. Okay, so you have to be careful as to how you are writing that. Clear? The questions?
Actually, user controls both steering and longitudinal velocity.
Of course, very important that user controls this. That's why he has to give an input. User controls that. But this factor is not controlled by him. Okay? This factor is not controlled by him. That is the whole thing. So when he presses his accelerator, in other words, which I shouldn't say because we are looking at steady state. Okay? So when the velocities are high, okay, his steering input has to be higher. Okay? In other words, you take a turn at 40 kilometers per hour or take a turn at 80 kilometers per hour, your delta is different, is a factor which is very important to understand. Okay. So note that the problem also is that when you increase the speed, what happens to delta? It increases. That means that much amount of steering input you have to give. So that is the time that you have to also consider when you look at understeer gradient. Clear? Okay.
Sir, is the yaw center always be in the center of the...
Yeah, because this our whole note that's how we had defined this whole model. Okay, so center of gravity location is the body centered coordinates. We have placed it at the center of gravity location, right?
While we seeing the direction stability, the yaw center is at the front axle. And this is
Which
the bit
is-
of front axle. While we studied that direction stability.
No. There we were just looking at the forces. We did not write down the equations. We are just looking at forces. Okay. Here we have put a coordinate system and we are looking at the equations based on these coordinate systems. Okay. Yeah. Fine. Now we'll digress a bit. We will look at state space technique. Okay. Remember that we had expressed before we went into this expressions on steady state, we were looking at the stability, okay, from the state space perspective as well. Or in other words, we were writing it before we went into the stability in terms of state space. Remember that we had written this as what is the state vector? V and R. Remember that we had written it in terms of V dot R dot is equal to A into VR, okay, plus some B into U. B is AC alpha F by M, C alpha F by M and AC alpha F by I and so on, okay. So state space becomes a very important vehicle to study vehicle dynamics. So in fact, many of the controls that are used are based on the state space techniques, okay, and it becomes very easy for us to even understand what happens for a given input, or in other words, how does the vehicle behave. Quickly, if you want to look at how the vehicle behaves, for example, if I give a step input or some other input, so that becomes extremely important. So let us now get into this state space, and let us now derive the expressions for, or I would say, brush your memory, okay, on state space. That will answer some of the questions which were asked as well. So let me write down the state space expression as note that when I put a squiggle at the bottom, it means that it's a matrix or a vector, right? That's all. Remember that B, for example, we just now said B is C alpha F by M, and so in other words, remember that B is C alpha F by M, AC alpha F by I. I is what we mean by I is Z, because we removed that, okay, and U is nothing but the delta. Okay, go back and look at that expression so that you can relate. A is a matrix which we wrote, you remember, minus C alpha F plus C alpha R and so on. Okay, that's the expression for A. So in other words, I am just abstracting that expression and writing down this form. So what's the first step now? The first step is to take the Laplace transform of this expression. Okay, so taking the Laplace transform so we are looking at a linear time invariant system. So A stays as it is. Right? Okay. So Si minus A xs is equal to x naught plus b us. Clear? So that xs, these are all which you have studied, is equal to clear? Okay. Now, in the same way as we give in the traditional control system space, let us name and name the inverse Laplace transform of psi s is equal to phi t. Okay? I'm just writing down a general framework from which we will get into specifics. Right? From which I can write down the expression for the xt. Okay? Just taking the inverse Laplace transform of 1, we can write down xt is equal to phi of t x of 0. Oh, sorry. I should write this as not 0, sorry, s x naught. Let me just x naught of s, not x naught. Okay, that is x at t is equal to 0. That's the input. So let me leave it as x naught. Okay, x of x at t is equal to 0. That's what is meant by x naught. That is the initial condition. Right. Okay. So I can write it as x naught or xs, but as long as you understand it, that's fine. Okay. So I can leave it like this, or I can put x naught. But please understand that that is the initial condition that I am. Actually, x of x naught is fine. Okay. So just note that that's the initial condition. Okay. So plus phi of t be u of t. Okay. Now we will develop what can be the expression for psi of s or phi of and a phi of t as well. Right? Let's develop that expression. So how do you develop this expression? Is this okay? I deliberately wrote that. I wanted to check how much of Laplace transform you guys know. Is that okay?
It's a linear system.
Is that okay? What is the Laplace transform of multiplication? You would have heard about this term. Convolution. Yes. You would have seen in your earlier classes that convolution is given by a star. Okay. So if I say phi of, let's say phi 1 of t convolution phi 2 of t. We will see in a minute what it is. A Laplace transform of the convolution term is equal to, in the Laplace domain, the convolution becomes a multiplication, right? So that would become s into phi 2 of s, right? So what is this term now? B is a constant, of course. So it is a psi of s when I put, okay, this is a multiplication. So what should I get here? I should get a convolution. Okay, I should get a convolution. Right? So be very careful when you write Laplace transform. Okay? So many people would leave out this term x of 0. Okay? Let me call that as x of 0. I'm very comfortable with that. So x of 0, that's the, so that x0 of s is not there, x of 0. Okay, many people leave this out. When I say Laplace transform, immediately x dot, I know x dot is equal to s of x, x of s. There is one more term. Like that, you just can't, blindly write it like this, and you have to look at when it's a multiplication, you have to write down, okay, the convolution term. How do you write the convolution term? 0 to t phi of t minus tau b u tau d tau. That's the convolution term. So that is the inverse Laplace transform. Okay? I will not say this again, and you have to make sure that you remember this. Right. So now we will develop a specific. I suggest that you go back and revise your Laplace transform, maybe look at the Laplace transform table once more, okay, because we may be using Laplace transform when I give an input, okay, different input, we will be using that. So you should be knowing how to convert it. So get back to your controls course and look at these things once in order to understand this, okay? Right. So I want to develop this, and let me look at a simple a differential equation, or ODE, which is the first order differential equation, and write down that expression. So x dot of t is equal to a of xt with an initial condition of, say, x naught. What's the solution for this equation? X of t e power a t okay, x naught, right? Now let us define a matrix, okay, which I would call as e power a t, which I would call as e power a t, in the same fashion as I would define e power, okay, a t when a is a scalar quantity. What is e power a t? What is e power a t? 1 plus a t plus a square t 2 squared by 2 factorial plus a cube t cube by 3 factorial, and so on. Let me define e power a t to be like that. That is now identity matrix plus a t plus a squared t squared by 2 factorial, and so on.
We should have one more u of t term, right? X dot of t is.
No, that's the expression if this is the expression, okay, if that is the, no, I have not come back to this, just wait a minute, right? I have not yet looked at it. We will, this is only to tell you like what e power a t looks like, right?
Before you erase that side, can you mark the critical velocity there?
Yeah. What's the yeah. So that's the velocity at which delta becomes 0, right? Remember that we had k1 into ay, for example, or m into bc alpha r minus ac alpha f divided by lc alpha f alpha r into u squared by r plus l by r. You know, this term, that what is there in the bracket multiplied by u squared by r, that term, if it becomes negative, okay, and beats this L by R, then only it becomes unstable. So at the point where both the terms are the same, that's the point. Clear?
After negative part, I am able to understand, but that part, that means you are going on a straight road.
No. This, please note that we are cornering. We are cornering. So imagine like this. I have a oversteered vehicle. Okay, I keep on increasing the speed. It is, say, for example, it's a round turner, okay, which you see in the street. Say, for example, you're going around, right? So you start with a velocity, then you give a steering input, right? And then you go around. Then you increase the velocity. Okay, forget for a moment steady state. Then don't get confused in that. Let's say that you increase the velocity. The steering which you have given, you have to now make it smaller. Now further increase the velocity. Okay, the steering input, again you will make it smaller. At one point of time, you are not going to give any input to the steering, okay, and the vehicle will go around at one velocity. Okay, you increase the velocity further, you will have to give the steering this side in order that you go in the clockwise direction. Okay, so that point at which you give zero input to the steering is that critical velocity. Clear? I suggest that there are a number of videos in the YouTube. Okay, go back and look at these YouTube videos where steering input is given for an understeer vehicle, an oversteer vehicle, and so on. Okay, it will become very clear. So we'll have a course next semester on vehicle dynamics lab, and in which you will also be studying, or you will be doing simulations as well as some testings as well. Right? Okay, let's get back to this. E power at. Why are we defining like this? The interesting fact is that this matrix has all the properties of e power at. Right. So if I now differentiate what is d by dt of e power at, a into e power at. Okay. Interestingly, when you differentiate this matrix, d by dt of e power at is equal to differentiate that, and you would see that it's the same. Right? Okay. So we are going to use this fact, okay, in order to understand what can be the expression for psi f s. And also the fact that e power at, the inverse of the e power at, is equal to e power minus at. Right? We're going to use that. We'll do that in the next class when we're going to substitute and give an expression. Clear? Okay. Any questions on this? Okay. Anyway, we will continue it once it's the duration will take one more class. Then we will be completely on board. Right? We'll stop here. We'll continue the next class.